Good afternoon, everyone, and welcome to the Lunar and Planetary Laboratories annual Summer Science Saturday. My name's Tim Swindle. I'm the director of the lab, and I'm thrilled to have all of you here, if only virtually, for this presentation about the OSIRIS-REx mission by Professor Dante Lauretta, the principal investigator for the mission. Those of you who've been to one of these in the past know that this year is different. Normally, when we have a lecture such as this, we'd have displays and hands-on activities for both children and adults throughout the Kuiper building, in particular in this atrium around me. And we'd have things on the mall, all tours of the building. We'd be partnered with other entities on campus. But it's pretty quiet in here today. The downside of being in the middle of a pandemic is that we can't get you to come to the place where we work or talk to you individually. But there is an upside too, actually a couple of them. One, our lecture hall behind me holds only 160 people, so that would be the limit to the number who could attend one of these lectures. But right now with Zoom, I see that we've got 220 participants signed on right now, and I know that there were another 100 RSVPs, so we're going to have a big crowd. In addition, I've seen in the chat that some of you are Zooming in from all over the country. Wouldn't be able to do that. And finally, another upside is that you don't have to worry about the weather. No concerns about monsoon rains or heat stroke or both. So in a way, this is a microcosm of our experience in the lab and at the university throughout the pandemic. We can't do things the way that we've done them in the past, but we've found that it's remarkable what we can get done. We still have world-class research like the OSIRIS-REx mission that you're going to be hearing about today going on. We still have teaching and learning going on, but we're doing many things in a slightly different fashion. I'd point out that if you'd like to keep up with the news of the science we're producing, I believe that the link is still on the screen. It's lpl.arizona.edu/news. And there's also a link if you're interested in investing in the success of this amazing organization, lpl.arizona.edu/invest. But now on to today's talk. First, let me explain a little bit about logistics. We will have a Q&A session at the end of Dante's talk. Those of you who are familiar with Zoom know that there are multiple ways that we could do that, but what we're going to do is use the Q&A feature. So you should see a button down at the bottom of your screen. You can ask a question at any time, but Dante will start working his way through the questions after he's finished the talk. So please use the Q&A for questions rather than the chat or raising hands. Dante will tell you a lot about the OSIRIS-REx mission, but there are a couple of things I wanted to mention in case he doesn't. This is a project that has been going on for close to 20 years now. Dante and others spent nearly 10 years designing the mission and writing a series of proposals before they finally got funded for the project, which is the largest project in the University of Arizona that the University of Arizona has operated. It's the largest in terms of dollars. We're in charge of something like $800 million, but it's also a very large project in terms of people. More than 500 people at the University of Arizona have worked for this project, including more than 200 students. So this is definitely a team effort. When Dante and I were discussing these numbers this week, he pointed out that one of the things he's proud of is there are 14 people who have started as students and have ended up with regular jobs on the mission. But it's a team effort, but the team has a leader, and that's definitely Dante. Dante Lauretta grew up in Arizona. He got his bachelor's degree in math, physics, and East Asian studies, yes, East Asian studies at the University of Arizona, before going on to get a PhD in Earth and Planetary Sciences at Washington University in St. Louis. He's been on the LPL faculty since 2001. He's won a number of awards. I won't name them all, but they range from individual scientific awards to teaching awards to awards for the OSIRIS-REx team to awards for board games he's designed. Dante, thank you for joining us this afternoon, and we look forward to hearing what you have to say.
Thank you, Tim. Can everybody hear me okay out there? I am excited to be here today to talk to you about the OSIRIS-REx mission. As Tim mentioned, we're really in unprecedented times, and it's bittersweet because this is our big year on the program. Tim mentioned the long timeline that we've been working on this program to try to get a sample back from asteroid Bennu. And it's really getting to be go time, as I'll tell you towards the end of the presentation. We've got a couple key flight activities ahead of us, and that sample is going to be safely tucked away soon and on its journey back to Earth. It's definitely a team effort. And I'd like to start out the presentations with a really fond memory. This was one of the last occasions where the team was able to get together in person with a crowd this large. And this was a science team meeting that we held in November last year in Tucson. And people come from all over the world to be part of our mission. And we're really excited to have partners from Canada, from Japan, from the UK and France, and many other nations around the world. It's a great team effort. Everybody brings a diverse set of skills and perspectives and really makes this incredibly complicated program so successful. I'm going to give you some background information on the mission. I assume a lot of you know a lot about OSIRIS-REx, but I'm going to start out the presentation by talking about the journey and how we got to the point where we're just about ready to collect our sample. And it goes all the way back to the scientific investigation of the mission. My role on this program started back in 2004 when I was actually invited by the director of the laboratory at the time, Dr. Mike Drake, to be the deputy principal investigator for the proposal effort. And my first job was to come up with the science investigation program for the mission. So I went home that night, really excited to be part of such an exciting endeavor. And I wrote down 4 words. I wrote down origins, spectroscopy, resources, and security, which I thought captured the 4 areas of science investigation that any team planning to go out to a near-Earth asteroid, study it in great detail, and get a sample would be interested in. For the origins, we're really interested in the dawn of the solar system. When you go to an asteroid, you're going to the oldest geologic record that exists, and that tells you the story of how planets came to be. We're particularly interested in asteroids like Bennu, and I'll tell you more about this throughout the presentation, because we think they're what we call carbonaceous. They're related to a rare type of meteorite called carbonaceous chondrites. We think those meteorites are fragments of asteroids like Bennu. And they're special because they have a lot of water, and the water is not ice, it's not liquid water that's moving around on the surface of the asteroid. It's actually ancient water that reacted with rock and created a special kind of mineral called clay mineral, or more specifically hydrated phyllosilicates for the mineral buffs out there, things like serpentines and chlorites. They also contain a lot of organic material in the form of carbon compounds, aromatic molecules, aliphatic molecules, more complex things like amino acids, nucleic acids, the kinds of things that build the biomolecules here on Earth. And we think the origin of life may have started by the material from these kinds of asteroids being delivered to the surface of the Earth and then growing into DNA and protein and kicking off molecular evolution, leading ultimately to us. For the spectroscopy side of things, there's hundreds of thousands, if not millions of asteroids in the solar system. And we're never going to be able to send a spacecraft to all of them anytime soon. So we study most of them with telescopes. And in order to understand their composition, to find the ones that have a lot of water, have a lot of organics, we use a technique called spectroscopy. And that's basically passing light through a prism or some other optical element that breaks it apart into its different colors or wavelengths. And different minerals have different intensities of light as a function of their wavelength. So you can identify the minerals that are on the surface of an asteroid using this technique. But we're going to something, because it has all that carbon, that's very dark and black. So the spectral interpretation is difficult. So we're going to bring a sample back to allow us to better understand the composition of these kinds of asteroids throughout the solar system. When I first wrote down resources almost 17 years ago now, I was really thinking sci-fi geek on display here. But in fact, the idea of going to near-Earth asteroids and extracting resources to further exploration has got some traction of late. We're primarily looking at that water, because water, as we all know, is hydrogen and oxygen. You can split that apart, making liquid hydrogen and liquid oxygen one of the most powerful rocket fuels that we know of. And all of a sudden, you've got gas stations in outer space. And then finally, security. We're going to an asteroid. From a dynamics perspective, it was relatively easy to launch a spacecraft off the surface of the Earth. And I say relatively because nothing about spaceflight is easy. Get to the asteroid, pick a spot, get down to the surface, get a sample, and bring it back. That means its orbit is very similar to the Earth's orbit. And that means it has a chance of impacting the Earth at some point in the future. In fact, our target asteroid, Bennu, is the most potentially hazardous asteroid in the solar system. with a non-negligible chance of impacting the Earth in the next 200 years. Don't worry, it's not going to happen anytime soon. And then as the mission grew, we became OSIRIS-REx, which is got that cool connection to the dinosaurs. And I like to call the last part of the mission name my backronym, the Regolith Explorer. Regolith is what we call the loose blanket of rock and gravel and dust on the surface of an airless body like Bennu. So before we launched, we knew a lot about this asteroid. As you can see over there on the left, there's two views of its orbit. The sun is at the middle of that diagram. This is where the planets and Bennu were on September 21st, 2018. And you can see the green circle is the orbit of the Earth, and the blue ellipse is the orbit of Bennu. And when you look down below, a more inclined view, you can see Bennu is tilted up about 6 degrees out of the plane, the orbital plane of the Earth. But right there around September, its orbit crosses that of the Earth. Its period, the time it takes to go around the sun, is 1.2 years. Earth is 1 year. So every 6 years, they line up, and Bennu does a close approach to the Earth. During those close approaches, we're able to train our telescopes on the ground and in space to get some really great information about the asteroid. And the data that you see over there on the right, kind of the speckly images, are radar returns from the Arecibo radio telescope in Puerto Rico. And we were able to see Bennu when it was discovered in 1999. And because it comes back every 6 years, we saw it again in 2005 and 2011. And we got Arecibo radar data on all 3 occasions. And we're able to process that data to determine what the shape might look like. And that's the model that you see on the far right that's spinning around there, based solely on the radar data. So before we even arrived, we knew it was about 500 meters in diameter, that it had this really interesting spherical, what I call spinning top shape. It's almost bulging at the equator. It's spinning around every 4.3 hours, and its obliquity is 180 degrees, which means that its south pole, its north pole points south compared to the Earth and most other objects in the solar system. So it's kind of rotating backwards. It's got a very low density of about 1,260 kilograms per cubic meter. That may not mean much to you, but you can compare that to your average rock, which is around 3,000. So you can see it's less than half the density of normal rocks on Earth or even most meteorites. And in fact, ice is about 1,000 kilograms per cubic meter. So it's much closer to icy material. And that's good news, because when you start to make clay minerals with a lot of water in their crystal structure and a lot of organic material, you drive the density of rocks lower. So right away, we had a good sense that we were probably onto a good target. It's very dark. Its geometric albedo is only 4.5%. That means that when sunlight hits the surface, 4.5% is reflected, 95.5% is absorbed by the surface. So it's very dark and black. And that's because we think it is rich in carbon compounds. And then finally, that's confirmed by its spectral type. When we look out at the asteroid population and we measure its spectral properties, we classify them in what I call the asteroid alphabet. Bennu is a B type, which we think, and have we since confirmed since arriving there, is linked to carbonaceous chondrite meteorites. The other thing we think about Bennu is that it's pretty small. 500 meters on the scale of asteroids is small, and that wouldn't survive the history of the solar system. It would probably get kicked out of the solar system, collide with a planet, or fall into the sun on timescales on the order of 1 billion years or so. So Bennu is most likely a fragment of a much larger asteroid that was shattered in a giant collision in the asteroid belt on the order of 1 billion years ago. And it's rubble that has kind of drifted into the inner solar system. And now that it's on this Earth-crossing orbit, it's very near the end of its lifetime. This is a very unstable region for asteroids to exist. Every time they make a close approach to the Earth or another planet, their orbit can be perturbed, sometimes substantially. Ultimately, it's going to end up colliding with one of the planets, or most likely falling into the sun. So we built an amazing spacecraft to go out and investigate this asteroid and to collect a sample. And this diagram shows you the different scientific instruments that we have on board. So starting over on the top on the left, we have REXIS, the Regolith X-ray imaging spectrometer. This is actually a student experiment. A group of students at MIT and Harvard came together, proposed this idea to us, and we accepted it and said, yeah, we're going to give you guys a ride to Bennu. You're going to be able to use your X-ray instrument to try to study the composition of this asteroid. Next, we have the 3 cameras that make up the OCAMS camera suite provided by the University of Arizona. In fact, built right here in the building that I'm giving this presentation from right now. We have the SAMCAM, which is about to be the star of the show. SAMCAM was put on the spacecraft to document the sample collection event. So it's watching as we go down to the asteroid surface to collect the sample. MapCam, as its name implies, is the workhorse mapping camera. And most importantly, it has a series of color filters. So we're able to look at blue, green, red, and infrared wavelengths specifically with the camera and get an idea of the color variation across the surface of Bennu. We also have the PolyCam. This has got two functions, poly meaning multiple. It can start out as our telescope, and we can pick out Bennu when we're over 2 million kilometers away from the asteroid during our approach phase all the way back in August of 2018. And more recently, as you'll see in this presentation, it's turned into a microscope, and it's given us amazing high-resolution images of the surface, which was critical for picking the site where we want to get the sample from. Then we have our two main scientific spectrometers. We have the thermal emission spectrometer, or OTIS, provided by our friends at Arizona State University. And this is looking at the heat that's coming off the surface of the asteroid. When you're in the infrared wavelengths that OTIS observes in, you're seeing emission of radiation as Bennu's surface heats up and then sends that energy back out into space as infrared wavelength light. And then we have OVIRS, which is the visible and infrared spectrometer, kind of picks up where OTIS leaves off at the short infrared wavelengths all the way to the visible light that we can see. This was built at the Goddard Space Flight Center, and both of these instruments provide information about the minerals that are on the surface of the asteroid. And then finally, over there on the right, we've got our laser altimeter, OLA. This was built and provided by the Canadian Space Agency. It's a scanning laser rangefinder that operates at very high frequency. And so it shoots a laser beam that bounces off the surface of the asteroid, and we measure how long it takes for that light to fly out of the instrument, hit the asteroid, and come back to the detector, telling us how far away that point is. And it does that 10,000 times a second. So we're very quickly building up amazing three-dimensional topographic data of the asteroid surface. And of course, all of that instrumentation is there to support the primary objective of the mission, which is to get 60 grams of pristine sample from the surface of Bennu. I mentioned earlier that we do have meteorites that we think might be related to asteroids like Bennu. We're really interested in understanding if these kinds of carbon-rich asteroids helped trigger the origin of life on Earth. The problem with meteorites is as soon as they land on the Earth, they're contaminated by microbes and bacteria. They're touched by people, usually in an uncontrolled way. And so when we're getting to the most interesting compounds, like the amino acids that make up our proteins or the nucleic acids that make up our DNA and RNA, we've got this enormous contamination signal that makes it hard for us to understand what's going on in the asteroid. So in order to overcome that, we want to make sure we understand any contamination that the sample got due to our activities. So we spend a lot of time both keeping the spacecraft hardware very clean before we launched, and even when we're in flight, we can do bakeouts by exposing the components to the sunlight. And then we also document anything that might have gotten onto the sample, either from thrusting with our rocket engines on the spacecraft, or during the launch event, or other things we might not think about. We have a record through witness plates about anything that might have contaminated the sample. And then we also have a separate strategy for collecting the material that's based on contacting the asteroid surface. So I love the picture that's over there on the right, because that kind of shows you the two different ways that TagSam, is what we call this device, the touch-and-go sample acquisition mechanism, will get material off the surface of Bennu. I also like, this is a pretty historic photograph. I think this is from testing around the 2012 timeframe, when we thought Bennu's surface was going to be like a beach. And I literally used that term with my team. We are going to a beachy asteroid. It's going to have a lot of sandy-like material. It's going to be really easy. Told them that over and over again to get this sample off of there. So the first thing you notice is where TagSam touched the surface of the test bed, the test soil there. And you can see a ring that's pretty flat, and that's a couple centimeters wide. That's the base plate, and on that base plate we've got contact pads. We did an enormous amount of testing to pick the material for those pads, and we settled on something fairly common, Velcro. We make it out of stainless steel, and Velcro has two sides. It has a hook and it has a loop. It turns out the loop side is the best. It kind of acts like tweezers. When you push it down under the soil, the loops expand away, and then as you come out, they snap back together and they grab particles up to 1 millimeter in size. The main collection technique has to do what was happening in the center of that image there. You can kind of see almost a moat surrounding a mound or island. TAG-SAM is basically a space vacuum cleaner. Vacuum cleaners work by creating low pressure inside the vacuum that pulls air through a filter and grabs all the dirt and other stuff, like at my house, Legos, for example, into the filter bag. Well, there's no air at Bennu. It's an airless asteroid. So we bring our own bottles of air. So it's like a vacuum cleaner in reverse. We open up one of those bottles, making a high pressure region underneath that head, which is that disc-like device at the top there, which is basically an air filter. And that air or nitrogen gas, high purity nitrogen gas, goes into the soil or the regolith, fluidizes the material, and it expands up into that filter, capturing at least 60 grams of material for us to bring home. And then how are we going to get that onto the surface? Well, the entire spacecraft is a sample collection device. So here's the TAG-SAM head coming down, making contact. When we made this animation, we also thought we were going to a nice beachy surface, firing that gas bottle, fluidizing the regolith, which expands up into that filter, up and away from the surface of the asteroid. That's why we are calling it TAG and TAG-SAM. It's a touch and go maneuver. We only expect to be in contact with the surface between 6 to 16 seconds and collecting sample for about 5 seconds. Once we verify that we have it, we'll actually take that entire filter, place it into a sample return capsule, and detach it from its 3-meter-long robotic arm. So that's the event that's coming up in October of this year. And now I'm going to step you through how we got to this point in our journey. So the journey to Bennu is kind of shown over there in our itinerary, starting with the launch at Kennedy Space Center in September of 2016. And the photograph that's over there on the left is one of the final views we got of the spacecraft before we put it inside the rocket's nose cone and sent it on its journey into the solar system. We spent almost 2 years between September of 2016 and December of 2018 getting to Bennu. In between, we had to get out of the orbit plane of the Earth. If you remember that orbit diagram that I showed you, Bennu is inclined 6 degrees relative to the orbit plane of the Earth. When you launch off the Earth, you're in the same orbital plane as the planet is, and you need to change it by that 6 degrees to a rendezvous with Bennu. And we couldn't afford the fuel that would be required to do that. We have a full fuel tank just to get the job done at Bennu. So we used the gravity field of the Earth as a slingshot. And when we approached Earth in September of 2017, we flew underneath Antarctica, and we popped up 6 degrees, allowing us to begin our approach phase in August of 2018. We went into orbit in December of 2018, and we've been characterizing this asteroid in amazing detail ever since, leading to our final site selection, which we announced in December of 2019. And now we're getting ready for the sample collection event this October, and then we can start to think about bringing it home. We actually can't leave the asteroid until March of 2021. We're looking at April right now as our departure date. We could actually slip that into May if we had to. It really is relative to where the asteroid and the Earth are in the solar system and how much fuel we have in our tank. So we have enough spare gas, so to speak, to leave any time in that April or May timeframe. If everything goes well and we get that sample in October, we should be departing Bennu in April. It takes another 2.5 years to come home, and the sample will be back on the Earth in September 2023, beginning the real exciting science phase for me, because I started out my career studying those meteorites in laboratories, the sample analysis phase, which begins 2023 and continues at least for 2 years as part of the OSIRIS-REx mission. The launch was an amazing event. September 8th, 2016, the skies above the launch site at Cape Canaveral, then the Air Force Station in Florida, opened up beautifully, sending OSIRIS-REx on its journey on the perfect Atlas V launch. These are just some of my favorite photographs from that event. And then since arrival, we've been going through a very intense series of operations. So this is kind of our timeline, starting out with that approach phase imaging in August of 2018, the arrival, which we marked as the orbit, the entry into the gravitational field or the heliosphere of Bennu in early December of 2018. We actually then flew around the asteroid a couple of times to measure its mass in a phase we called preliminary survey, and then we did that orbit insertion on New Year's Eve of 2018. That was kicked off the orbital A phase. And we actually got a couple Guinness World Records for that activity. And when I say we, I really mean the OSIRIS-REx spacecraft holds a Guinness World Record for the smallest orbit ever around a planetary body, which has been down to about 450 meters from the asteroid's center of mass over the course of the mission. And actually, asteroid Bennu has a Guinness World Record for being the smallest asteroid ever orbited by a spacecraft, at least one from Earth. So after orbit A, one of the things that's cool about this mission is the gravity field around Bennu is so low, we can go in and out of orbit as we please. And in fact, we have to do that to get some of the amazing data that I'm going to show you. And so we left orbit to do a campaign called Detailed Survey, which we broke up into 2 different phases. The first one, called the baseball diamond, so named because we needed a wide range of viewing conditions. And when we first designed it, it actually looked like we were running the bases of a baseball diamond. It got redesigned, but the name stuck. And we got an enormous amount of information from the camera systems about how Bennu looks under different shadowing conditions and different illumination conditions and different spacecraft positions. Then we kicked into the equatorial stations, where we produced global spectral maps of the asteroid. A couple more orbital phases where we measured the gravity field of the asteroid and some unexpected phenomena that I'll talk to you about. And then we got into a reconnaissance phase where we started to have areas of interest on the surface that we wanted to look at in great detail, leading us up to site selection in December of 2019. Since then, we've been looking at both a primary site called Nightingale and a backup site called the Osprey through closer reconnaissance, Recon B and Recon C phases. And now we're ready to go. We've completed our first rehearsal of the sampling attempt called the checkpoint rehearsal in April. And we're getting very close in 10 days, August 11th, to the second rehearsal called the matchpoint rehearsal, leading up to that first sample collection attempt in October of this year. So let's take a look at this asteroid. We got some amazing data. Here you can see some of the first really high quality images that we got of Bennu on our way in on December 2nd, 2018, right before the so-called arrival date. Here we're looking at the entire asteroid as it rotates in front of us with a pixel scale of 33 centimeters. Remember, it's taking 4.3 hours to go through the rotation that you see here. And then the phase angle is 48 degrees. The phase angle is the angle between the sun, the asteroid, and the spacecraft. That's good because you kind of get some really nice shadows. In fact, if you look over on the right side of the screen there, you can see where the terminator is, like the 6 p.m. point of the afternoon. And that really shows you like crater rims, and some of the big boulders really pop out under these great imaging conditions. So I mentioned early on when we were planning, designing the mission, we were expecting a beach. And that's what I told the team to design the mission to. And that was based on telescopic data, primarily its thermal properties, how quickly it heated up and cooled off, something we called thermal inertia. And then these data came in. And the first thing I thought was, yikes. We got a real challenge on our hand. This is not a beach, right? This is a very rocky, very rugged surface. You can see large boulders on the surface. There's really no immediately obvious patches of fine-grained sandy material like we were hoping to collect. The good news is TAG-SAM is designed very well, and it can pick up samples as large as 2 centimeters across. So we don't need sand, but we do need gravel. And so the hunt was on to find the best location on the surface to go get that sample from. Along the way, we're able to determine its shape even more precisely by a long shot than we had from the Arecibo radio data from the Earth. And we found out, actually, we did really well. Arecibo and the radio astronomers who put that information together definitely nailed Bennu's spherical spinning top shape. So here we're looking at a couple different views of the asteroid. On the upper right there, we're looking right down at the North Pole where all that red high geopotential landscape is. And then as you move towards the equator, shown better even on the image on the lower right there, you get to the geopotential lows. And gravity and acceleration on a body like this are completely counterintuitive. In fact, the equator, as we saw, bulges out relative to the poles. It's like kind of squashed. Yet the altitude at the pole is higher. That's because Bennu's rotation of 4.3 hours imparts enough centrifugal force to make it a very low acceleration at the surface of the asteroid. So the way to think of the geopotential is if you put a marble at the North Pole, it would actually roll down the surface of the asteroid until it got to one of those dark blue patches that you see near the equator. Once we have the shape, we can determine a volume. And then when we fly over the poles and the equators during that preliminary survey phase, we measure how much Bennu pulls the spacecraft towards it through its gravitational force. And we're tracking the spacecraft through the antenna and receiving the data back here on Earth at a deep space network station. We call that radio science because you can measure that acceleration, that attraction between Bennu and the spacecraft, and that tells you how massive it is. And you combine the volume from the shape with the mass from radio science, and you can calculate a density. And we got 1190 kilograms per cubic meter, very close to that 1260 and well within the uncertainty that we got from our ground-based observations. Even lower density than we thought. And as a reminder, your average rock is on the order of 3,000. So what is that telling us? Well, clearly Bennu is a pile of rubble. We can see large boulders, some of them with very different brightnesses and compositions scattered across the surface, some up to 100 meters, many of them at the meter scale. It's definitely a pile of stuff that accumulated under its own gravity. And that's exactly what we predicted in terms of its origin. Remember that little movie that I showed where one asteroid collided with a larger one, creating thousands and thousands of fragments. Some of those collapse back into each other, creating these rubble pile asteroids. The original asteroid was probably much bigger, 100 kilometers in diameter or so, and this is just one little piece of it. And there's probably thousands of other asteroids like Bennu that are related to that same collision. And when that happens, we call those asteroid families. So we think Bennu is like this, and it's probably got a lot of void space kind of cave network inside of it. So I bet about half of it is empty. So it still doesn't get you up to that average rock of 3,000, but it gets you close to clay-bearing rocks, which are like 2,000 to 2,200 kilograms per cubic meter. And then the big question, where did we misinterpret our data? So we thought Bennu was going to be a surface like a beach. And that was based on this property called thermal inertia. And inertia is resistance to change. So if you go and you try to push a large rock, you're going to take a lot of energy just to get that thing moving. You have to overcome its inertia. Thermal inertia is resistance to change in temperature. So if something has a very high thermal inertia, it heats up and it cools off very slowly. That's typical of large boulders. If it has a low thermal inertia, it heats up and cools off really fast, like a beach. Many of you have probably been at the beach on a nice sunny day. Very quickly, that sand is hot, and you got to get your flip-flops on if you want to get to the hot dog stand for lunch. By the time you go out right after sunset, the beach is nice and cool. But if you go sit on a large boulder, you'll feel that heat radiating off of there. Bennu has a very low thermal inertia. Its value is 350 in these crazy units that I have on the slide here. We just call those SI units or standard units. Because it's basically a combination of the heat capacity and the way that heat conducts through the rock. And when we got there, we found out, you know what? We did a good job. We measured the thermal inertia properly of the asteroid, but we expected that to be beachy sand-like particles. And it turns out that no, it's full of boulders, but it has a low thermal inertia. And in fact, the largest boulder on Bennu has the lowest thermal inertia. It's exactly opposite the trend that we had predicted from studies of Earth and a lot from studies of Mars. And this is just giving you one shot of what the surface of the asteroid looks like here. So it's dominated by meter-sized boulders. They're everywhere. This is one of the cool polycam images, and you can see one of my favorite rocks on the surface there, that big dark boulder with a white flake on its shoulder. We call this the gargoyle. In fact, that's its official name, approved by the International Astronomical Union. So that's the gargoyle boulder, and that's about 15 meters tall. The whole field of view of this image is about 70 meters. The other thing you start to look at here when you get these nice high-resolution shots is not everything looks terrible. In fact, just over the gargoyle's shoulder there on the left, you can see an impact crater. It's an oblique shot. But it looks like that might be finer grained material than the average surface of Bennu, which is dominated by these large rocks. So right away, from a scientific point of view, everybody's excited because one of the best times in your scientific career is when the system doesn't behave the way you predicted it to, because now you got a new problem to solve. So the team, especially we have a group called the Thermal Analysis Working Group, has been off trying to understand. We got the thermal inertia right. We got the grain size interpretation wrong. What's going on? it looks like the boulders on Bennu have very low thermal inertias. So they must be really porous and fragile, friable. In fact, when we look at the gargoyle, if, what I call his feet, which is the lower part of the image there, kind of like two triangles pointing down, there's a bunch of pieces that look like the gargoyle boulder. And in fact, that's a down slope. Those things are tumbling down towards that equatorial region. Gargoyle's about 10 degrees latitude right now. So we can even see evidence that the rocks might be breaking up on the surface. Again, consistent with them having very low strength, therefore very low heat capacity and thermal conductivity and low thermal inertia. Different than any rocks that we're familiar with here on Earth or on Mars. There could also be covering of dust, so we could be looking at really small particles, but it's a very fine coating. It could be a combination of these things. It could be that the regolith is kind of in between all the rocks. And in fact, when you start to look at this picture, you do see there are smaller grains distributed in between the much larger boulders. Bottom line was we still had work to do, and the thermal data, we were hoping with the OTIS instrument to be able to go use that to map thermal inertia at a much higher scale and drive us to the spot that we wanted to go get the sample from. That was tossed out, and instead the thermal scientists went off to solve this interesting new problem. So now we're focusing on our mineralogy. So we take a look at first the OVIRS instrument. OVIRS, remember, goes from the visible to the infrared wavelengths. Your visible wavelengths are down here. The graph shows wavelengths in microns or micrometers, which are 1/1,000,000th of a meter. The things you can see with your eyes are down at like 0.4 to 0.6, 0.7, 0.8. And so here at 2 microns, we're actually in the near infrared. You couldn't see this light with your eyes if you were at the asteroid. But there's some really interesting information about minerals and chemicals in this region. Especially, you can see Bennu is that blue spectrum that's at the top. And it's coming along. It's pretty flat, 2.2 microns, 2.4, 2.6. And then you get to 2.7 microns, and it drops off. And then it kind of slowly recovers back to what we would call the spectral continuum. We know exactly what's causing this because we see this in meteorites and minerals on Earth. This is due to water in hydrated minerals. Clay minerals, one of the first discoveries that we made on our approach to Bennu was that we literally hit asteroid pay dirt in the literal sense, that we got the kind of material that we're hoping to bring back to study here on Earth. Very water-rich, clay-rich material that looks like some of the most rare carbonaceous chondrite meteorites on Earth, like the Orgay CI chondrite down there in the bottom right, an Antarctic meteorite called Allen Hills 83100, and the very well-known Murchison meteorite, which landed in Australia in 1969 and has been intensely studied for its organic chemistry. So that's great news. Bennu is water-rich with a lot of clay minerals, and by analogy with these meteorites, probably also organic-rich. We get additional information about the minerals that are on the surface by looking at the OTIS data. First thing OTIS told us right away, you can see a bunch of meteorites compared to Bennu over there on the right. It also confirms OVIRS data that, yes, Bennu looks like these really rare CI and CM carbonaceous chondrites. I got a couple other meteorites plotted there at the bottom. The very famous Allende meteorite, which fell in Mexico, also in 1969, is a carbonaceous chondrite, but doesn't have a lot of water and doesn't have a lot of organic molecules. And you can see it looks very different. One of the things we look for is the bottom of a spectral feature where it kind of bottoms out and then starts to rise again in intensity, or in this case, emissivity. So you can see where we drew the dashed line is where Bennu's wavelengths start to drop off. And then you can trace the center of those peaks and you can see very different structure, very different location of the spectral absorption. So that looks like clay minerals as well in the OTIS data. The other thing that we saw was evidence for a different mineral, an iron oxide called magnetite. These are common on Earth. We call them lodestones. They make magnetic compasses early in history. And this is consistent with the clay minerals. A lot of times when you have intensive aqueous processes, high temperature water reacting with rocks, your iron will go into the oxide phase. And in these meteorites, we see a lot of this mineral magnetite. So everything looks good. Bennu looks like our carbonaceous chondrites, meaning at some point in its past, you had liquid water in the interior of an asteroid. And you remember, Bennu is only 500 meters across, and that's way too small, first of all, to survive the history of the solar system for 4.5 billion years, but also to have this kind of large-scale geologic process occurring. We're talking about hydrothermal alteration, the kind of things like on Earth that produce ore deposits. But that's completely possible in a much larger asteroid, like that 100-kilometer body that we think Bennu is a fragment of that was shattered on the order of 1 billion years ago. What happened there was probably very early in the history of the solar system. Bennu's parent object was bringing in rocks, bringing in metals, which are common meteoritic minerals as well, organic material, and ice, water ice, maybe carbon dioxide ice, and other ices. And then as you built this 100-kilometer object, radioactive elements in the interior started to decay, the system got hot, and that ice melted and started circulating in the asteroid, reacting with the minerals and producing the clays and the magnetites that we see today. One of the greatest parts of any exploration expedition like this is what surprises you. And so I mentioned that we went into orbit on December 31st, 2018. Less than a week later, on January 6th of 2019, we saw a completely unexpected phenomena. Bennu was basically shooting back. Particles were launching off the surface in ejection events. And you can imagine our first response was a little bit of caution. We were like, okay, what's going on? We're getting images like the one that I'm showing you here, where you can see the limb of Bennu. This is actually two different images. The lower left portion there, where you can see the asteroid, is a low exposure image. And then you can see a stream of particles kind of right at the edge of the terminator that's going up to the upper right. That's a short exposure, a long exposure image to bring out those smaller particles. And then we put those two together to make this image here. This was really exciting. It's like, what's going on? Is Bennu a comet? Could be like a really small comet. Are we seeing some kind of eruption event? Are we seeing some kind of fracturing event going on? So this kicked off a whole set of scientific investigations that we didn't plan for, but were presented a great opportunity. One of the cool things that we were able to do is we saw these particles across multiple images. So this is a simulation of that event, of a particle ejection event. And we're able to track where the particles went after they were lofted off the surface in those ejections. And so you can see there's some trajectories that are just going up to the upper right and off the screen. And those are escaping Bennu. Those are now interplanetary dust particles. They've left the asteroid, and they're independently flying in orbit around the sun. But most of the particles aren't doing that. You can see most of them are actually lofting off the surface, and they're going through these long arcs and landing back down on the surface of Bennu. Astute viewers might note that the ejection event happened in the afternoon, right? And so the particles are moving around, and they're mostly landing on the night side of the asteroid. We've seen dozens of these ejection events over the past year or so at the asteroid, and almost all of them are happening in the late afternoon like that, which gives us some hints about what might be happening on the asteroid. This has provided a scientific bonanza, so we're able to use these particles to probe the gravity field of the asteroid, understand the physical properties of the particles, how they respond to radiation pressures, and of course, get these great trajectories. So what do we think's going on? We actually still have 3 candidates that are viable, and in fact, all 3 of these might be happening. Especially the third one there is kind of a second order effect. So the 2 leading ideas for the particle ejection events, one is micrometeoroids impacting Bennu. If you've gone out stargazing, you've probably seen shooting stars. Those are fine particles of dust that are hitting the top of Earth's atmosphere at very high speeds. And those are abundant throughout the inner solar system. They mostly come from comets. Some of them come from a population of bodies called active asteroids, which is what we think Bennu is like. Active asteroids are asteroids that shed dust through a variety of different mechanisms. So when we put the particle trajectories together, we were able to constrain their masses. We got an energy, and we calculated that the average energy of these events is on the order of 100 millijoules. Very, very tiny energy required. It's that microgravity environment that makes it so easy to kick stuff off the surface. We see big events happening every couple of weeks at the asteroid, and Bennu's getting hit by a micrometeoroid with the energy in the particles every minute. So there's a lot of these things colliding with the surface of the asteroid. When we go to something happening every 2 weeks, that's like a 5,000 joules. So a millijoule is 1/1000. So we're talking orders of magnitude more energy is dumped into the surface through micrometeoroids every couple of weeks. And that's consistent with the afternoon because that's the leading hemisphere of Bennu. Bennu's traveling around the sun, and that's the direction, like the windshield of the asteroid, where most of these impacts would be occurring. The other idea is that it's related to the temperature. We showed you that great temperature map. Bennu's getting very hot and very cold every 4.3 hours. And that creates a lot of stress on the rocks. They expand and they contract over that very short time frame. And so you can build up fractures and you can dehydrate those clay minerals, causing what we call exfoliation, which could eject material into orbit or away from the asteroid. And then some of them we see coming off in the middle of the night on Bennu. And that could be secondary surface impacts. You saw in that movie that the particles leave in the afternoon, but they hit at the night side. And then you kind of get like the knock-on or tiddlywink effect, where one particle hits and it launches another one. And so it's kind of like popcorn on the surface of the asteroid, where things can be popping off. You have one big event, and that triggers a whole series of little events. We were able to rule out some of the other mechanisms that I list on the slide here. I won't go into those in detail, but those are the three that we think are probably most likely going on. So now let me move to our site selection. We really spent a lot of time analyzing our global data from the spectrometers or from the cameras to think about 4 different properties of the asteroid. First, can we get there, get to the spot we want to go to? Is it deliverable? If we go there, is it safe for the spacecraft, or is it potentially going to contact the asteroid and damage something? If we can get there and it's safe, is it sampleable? Is there anything for TAG-SAM to pick up? It has to pick up rocks that are 2 centimeters or smaller. And finally, is it the most scientifically valuable area of the asteroid to get material from? So we made 4 different maps that kind of characterize the surface under these considerations. We combined all of those together for our sample site selection. And by December of 2019, we had identified 4 areas of interest. I'm going to show it to you here. First off, I want to just highlight the laser altimeter data that we put together to make these amazing 3D topographic presentations of the asteroid's surface. On the upper left there, we got the Nightingale, then the Osprey, the Kingfisher, and the Sandpiper. You might notice that they're all birds. Bennu is actually a mythological bird from ancient Egypt related to the Egyptian god Osiris. And everything on Bennu is named after mythological birds or bird-like creatures. So when you take a look at these, you can kind of see that the surfaces are distinct from the background rough and rugged boulder-rich areas. And in fact, the Osprey crater is the one that we saw over the shoulder of the gargoyle in an earlier image. So we had 4 that we were evaluating against each other, and they each had their pros and cons. Basically, we were looking at where can we get the sample. Nightingale looks great. Nightingale is the closest thing to a beach that exists on the surface of the asteroid. But it's also got some really hazardous stuff around it, particularly if you just look over to the right of the Nightingale crater, you see a large rock that we call Mount Doom, because it's scary. We got to fly the spacecraft over that and then drop down to the asteroid surface to get the sample. Osprey is almost the opposite. It doesn't look that sampleable. The rocks in generally are pretty big, like 10 centimeters or so in that crater, even though they look small in this image. That's just because all the other rocks are 5 meters or larger around it. But it's really safe. There's no Mount Doom. That gargoyle is far enough away that we don't have to worry about flying the spacecraft into it. And in fact, those are our top 2 sites. The Nightingale, best one to get a sample, but it has some hazards around it. Osprey doesn't look so good for picking up a sample, but there's very few hazards that we have to worry about. So let's just take a closer look at them. These, again, what we've done to produce these products is we have the laser altimeter data from OLA, which scanned the surface, got us 5 centimeter resolution, and that crater is about 20 meters across. You can see Mount Doom in the upper right there as we kind of spin around, but you really get a sense that the interior of this crater does look like the most beachy terrain on the asteroid. It is definitely the spot that we want to go to get TAG-SAM down on the surface and collect that material. It does have some things we need to worry about, not just Mount Doom, but you can see several other boulders inside the crater there. Those aren't going to really damage the spacecraft on their own, But what they could do is they could cause the spacecraft to tip over and then fly into the Mount Doom. So we also worry about contacting those areas. Same kind of view for Osprey. You can see we got that nice, interesting white flat boulder. It actually has some of the exfoliation textures. You see a kind of a dark line cutting right across it. That's a step, which looks like some of the particles might have ejected from something like this before. And then this is about the same scale as Nightingale. The crater is about 20 meters across. And you can tell right away that it does look more rugged, but there's no Mount Doom on the horizon there. Gargoyle just barely visible in the upper left in this field of view. That black patch in the center of the crater looks kind of like Nightingale, and that might be the most sample, but that's pretty small. That's only a couple meters across. So Osprey, safe. We can definitely get the spacecraft down there. Even those larger rocks, we don't worry about tip over as much because there's nothing big for us to fly off into on our way back from the asteroid surface. And then we look at the sampleability. We quantify the sampleability of these two rocks. We do this a couple of ways. We use the tilt of the surface because TAGSAM is a rigid device and it can only be tilted about 14 degrees off the surface. And then we actually count every rock that's visible in the high resolution images from these sites. And we combine those two, compare it against laboratory data to give a sampleability assessment. And in these maps of both craters, blue is really good and red is really bad. So you can see in the center of Nightingale, it looks really good. And then there's two circles. There's a blue circle and a yellow circle. Those circles are where we're most likely to hit inside. It's an 80% chance we're going to land inside the blue circle and a 99% chance that we're going to land inside the yellow circle. Osprey doesn't look bad. There's some sampleable stuff in there, but we're most likely to hit the center of the circle. That's the most likely area, and then it gets lower probability as you move radially away from that point. And right in the center of Osprey, the sampleability is terrible. So there's a good chance we'd make it to the surface of Osprey, but not get the material that we're hoping to collect. So Nightingale is the primary site, and we've gone on to do high-resolution coverage. These are just some amazing images. Here is data from the Recon B pass, where we got about 600 meters from the surface of the asteroid, and now we're getting pixel scales of about 0.8 centimeters. So you're looking at rocks there. Some of them are on that 2 centimeter size range, up to a few 10 centimeters or so. This is kind of in the heart of the Nightingale site. Similarly, we went down to 250 meters, 225 meters from the asteroid surface for Recon C, and we got pictures of the asteroid surface at 0.35 centimeters per pixel. And you just got to stop and imagine what that actually represents. So here we are on Earth. We're operating a vehicle that's 100 million miles away or more, depending on where we are in the mission. We're doing precision guidance with a microscope, and we're taking pictures with 3.5 millimeter per pixel resolution. So a rock in this picture that's 6 pixels across is 2 centimeters and sampleable by TAGSAM. And there are a lot of them. In fact, I wouldn't be surprised if some of the rocks that we're bringing back to Earth are apparent in this image right now. It'll be a real fun puzzle when we're in the sample analysis phase to say, can we identify a rock in our laboratory against the rocks that are in these images here? So this just shows you the Nightingale site. Again, now I've got the 80% probability circle drawn in blue, and then the red circles are the size of TAGSAM. The outer diameter and then the inner diameter, because remember we have that contact plate there. And so it looks pretty good. It's actually fun. One of the things I like to do is I like to take the TAGSAM head, zoom in on the picture, and then kind of just imagine the sample that I'm going to get back if TAGSAM touched down in various locations across the surface. And then I'm really proud of this data set. So we've had a great team of scientists here at the University of Arizona. Tim mentioned how many students have worked on the program. We had a lot of our undergraduate students start out as boulder counters and particle counters, and they have become masters of this technique. So they can take an image from OSIRIS-REx, and they have GIS software where they indicate the long axis, the longest dimension of the rock, and then we map it. So the good news is that anything that's colored yellow in these boulder counts is less than 2 centimeters across. And there are a lot of them, and you can especially see that there are a lot of them towards the center of the Nightingale site. And then as you go over, look over on the left, so on the right, I've only got the 2 centimeter rocks plotted, and then on the left, all the rocks that were counted. up to 7 centimeters in blue, up to 21 centimeters, which would actually block the tag SAM inlet, because that's the inner diameter, in orange, and greater than 21 centimeters in red. So Nightingale looks good, and we actually can verify that the kind of material that tag SAM can pick up is present on this location on the asteroid surface. And we're able to use that to update the sampleability map for Nightingale. We got that great OLA data. Now we got these super high resolution images, and it's looking reasonably good. There are some areas that we're not so comfortable with towards the center, but right in the middle of the site, it's blue, it's good, and around there, it's good as well. And one of the things we don't take into account here is we don't know how the surface is going to move when we make contact. Remember, we're in microgravity, so this isn't going to be rigid. If it really is gravel and pebbles, it's going to flow like a fluid. So we expect, even though you see some red in the center of Nightingale, when that big, heavy spacecraft, or I should say massive spacecraft, makes contact with the asteroid surface, we're expecting you're actually going to get some of that stuff complying and pushing away, and hopefully revealing even more sampled material underneath it. So we've got our site, we got our backup site, Osprey, and now it's go for tag. So we're taking a very methodical approach here. In April, we did a checkpoint rehearsal. So to get to the surface of the asteroid, we have to fire the rocket engines in 3 occasions. We're in orbit, and then we do an orbit departure maneuver. And then we get to a location called our checkpoint, where we fire thrusters, which starts dropping us down towards the asteroid's surface. And we rehearsed those first 2 maneuvers back in April. And we got these images. This shows you what SAMCAM can see. So right in the middle of the image is the tag SAM. You can see the bright outline of the air filter. The gas bottles are actually wrapped up in that black Kapton mylar just to keep their temperatures controlled better. And so we're going to get this kind of information all the way down to the asteroid surface. And as you watch this sequence of images, you can see we're going right over Mount Doom, and then Nightingale crater is showing up right at the top of the frame towards the end of the sequence there. We also have navigation cameras, which help guide us in. We have some really great software on the spacecraft that's going to help us avoid those hazards and make sure those maneuvers at checkpoint and then match point go according to plan. And that's what's up next. So on August 11th, we're going to do our second rehearsal. We're going to actually implement the 3rd maneuver. So we'll do orbit departure, checkpoint maneuver, match point maneuver. That's coming up very soon. And we invite you to follow along with us on social media during that exciting event. And assuming that goes as well as the checkpoint rehearsal did, we are on schedule to get to the asteroid surface and get that sample from Nightingale on October 20th. And what do we think is going to happen? I like to advertise this. It's not guaranteed, as you've seen in the data. There's some hazards in the area. There's some big rocks. We could have a worst case scenario at Nightingale where we actually contact something that's bigger than 21 centimeters and it blocks tag SAM from picking up anything. So what do we think is going to happen? Well, we put in some safety nets into the spacecraft. The spacecraft knows what Nightingale looks like, and it's taking those navigation camera pictures, especially on the final few meters down to the surface, and it's predicting where it's going to contact, and it's going to make a decision. It's going to say, am I going to contact one of those hazards or not? And if the answer is yes, it's going to wave off. One of the nice things about microgravity is this isn't like landing on Mars where it's go or not. We have the chance to reset. The spacecraft is smart enough to say, I don't like this. That looks like I'm going to hit a hazard, a known hazard, Mount Doom or something, probably more likely one of those smaller rocks. Let's just fire thrusters back away from the surface and try this again. Right now, with all of our calculations and simulations, we think there's about a 9% or less chance that that's what's going to happen. We're going to get down to 5 meters from the surface. Spacecraft's going to do that calculation and say, waving off, going to get back in touch, and we're going to figure out how to do this. We think that there's about a 30% chance that we're actually going to make it all the way down to the surface, fire the tag SAM gas, but not get the 60 grams. Because as we showed you, there are some areas with bigger rocks, and we may not pick up the amount of mass that we want to. The likelihood that we're actually going to hit somewhere that's not safe for the spacecraft is very low. It's less than 1%. And then there's always the chance that there's like a processor reboot on the spacecraft or something, just what we call a fault that sets the spacecraft into safe mode. That has not happened since we've arrived at Bennu. We think it's a very, very low likelihood event. And then the last column of the table talks about what the surface response would be in any of these cases. So The first thing to take away is the most likely outcome in October is that we're going to make it to the surface and we're going to get the sample. We're saying that's at least a 60% chance or better of that outcome. But if we do make it to the surface and we don't get 60 grams, we probably have moved a lot of stuff. There's a lot of energy in Tag Sam's gas bottles, which means that the hazards are now going to be in different locations, and our hazard map, which the spacecraft is using to make that final calculation, probably isn't true anymore. So we're either going to have to create a new hazard map, or we're going to Osprey, and that's why Osprey is the backup site, and that's why we've done all of the same calculations for the hazards around Osprey, and we would go there for a second attempt. Same problem if we make it all the way down to 5 meters and the spacecraft waves off. You have to fire the rocket engines for that to happen. Those thrusters are going to hit the asteroid surface, probably also disturb it, probably also going to Osprey for the second attempt. And then the likelihood that we have unsafe contact and the spacecraft experiences an anomaly, also probably likely to disturb the surface because we're still going to fire thrusters to get away. So the only abort that would allow us to get back to Nightingale is if we have one of those spacecraft safe mode entries, and we actually are above 25 meters, we fire the thrusters, Nightingale's fine, and that in that case we would reset and try to sample at Nightingale again. Okay, so that's where we are. I know that was a lot. We're at the top of the hour. This is where you can learn more about OSIRIS-REx. Please visit our website at asteroidmission.org or nasa.gov/OSIRIS-REx. We're also on Facebook, Twitter, Instagram, and YouTube with lots of great content for you to engage and explore our data. So with that, I am going to take a look at some of the Q&A. I got that in a separate window. I'm going to bring that over here and see what we got. Okay, Steve Langford has asked, do you plan to leave the asteroid in such a way as to push it into a more distant orbit? We are not doing anything to intentionally change the orbit of Bennu. We're not capable of that. Bennu is like a mountain in space, and we're like the size of an SUV. So we are not going to be able to change its orbit. The good news is, from the impact hazard perspective, the impact with the Earth, which the probabilities only really start in 2150 to the 2180 timeframe, way in the future. This is something for future generations to worry about. What I'm excited about is we're giving them the information that the next mission, if it's going to be a Bennu deflection mission, they're going to have everything they need to know to figure out how to do exactly what you're asking, Steve. So let me see here. I answered that live. I'm going to move that over to done. David Herrera says, does the fact that its density is half of regular rock imply it may burn faster and not hit the surface in the unlikely event of entering Earth's atmosphere? This is a great question, David, and absolutely. One of the things I'm most excited about is when we're looking at the surface of the asteroid and we're analyzing this thermal data and we're trying to understand why we misinterpreted it early on, that low density means this stuff's probably really fragile. And I bet a lot of the stuff that may have been ejected from Bennu and intersected the Earth was lost in the atmosphere and destroyed. So I think there's a really high probability that we're bringing back something from the surface of the asteroid that is not represented in the meteorite collection, primarily because it probably destroyed easily during its entry into Earth's atmosphere. Thank you for that great question. Alana Wallace says, how far away is Bennu from the Earth? Asking because it takes 2.5 years to get there and back. If you think back to the orbit diagram I showed early in the presentation, Bennu's distance from the Earth varies enormously over the course of the 6-year phasing period between the two. There's times, and in fact, we're predicting in the year 2135, so 115 years from now, Bennu's going to pass in between the Earth and the Moon. And as we've talked about an impact hazard, even farther out in the timeline, say 2180, Bennu may be hitting the surface of the Earth. So there, the distance would be 0. In the case of in between the Earth and the Moon, it's about half a lunar distance. But it also can get really far away from us because it can be on the other side of the solar system. In fact, that's pretty close to where it is right now. So it can be over 2 astronomical units away. We're on one side of the sun, so you got the Earth, you got the sun, and you got Bennu. So when we're talking to OSIRIS-REx these days, we're actually talking across almost the entire Earth orbit, even a little beyond, because as we saw, Bennu gets out past the orbit of the Earth. The reason it takes 2.5 years is because it's not a straight shot from the asteroid to the Earth. We also are in orbit around the sun, so it's kind of this cycling game where we're going around and the Earth's going around, and we all got to end up at the same place at the same time. And that's why it takes us 2.5 years to get from the asteroid back to the surface of the Earth. Michael Mikowski says, you designed the TAG-SAM collector assuming a specific type of surface, which turned out to be only a tiny portion. What have you learned from this that can be applied to future sample return missions? Well, I think the good news is that we built a lot of what we call margin into the design of the spacecraft. So future sample return missions, they're definitely going to benefit from us, because now we've got not only Bennu, but our colleagues in Japan at the JAXA Space Agency have flown the Hayabusa 2 mission to asteroid Ryugu. And in fact, they're on their way home with a sample right now. And Ryugu and Bennu, it's fascinating to compare them. They look similar, but they've got some really outstanding differences as well. One thing they have in common is a rough, rugged, rocky asteroid surface. So I think anybody that's planning a sample return mission to an asteroid where you don't have spacecraft data, you got to think about picking up some big stuff. Centimeters. I wish I could pick up a meter-sized rock off the surface of the asteroid, because we would learn so much from something of that size. Okay. Bob Holmes says, how can you be certain that the collected sample is representative of Bennu and not a piece of something that has been attracted to the surface? Great question, Bob. That is what our spectrometers are telling us. So we've got beautiful spectral maps from OVIRS and OTIS. Couldn't show you those today, unfortunately, because we're just getting ready to publish them, and they're under embargo by the publisher. But we're going to see some really cool chemical mineral maps of the asteroid here soon in publication. So we can tell, how does Nightingale compare to the asteroid surface? And it actually does look a little different. I mean, you can tell right away it's kind of a unique feature on the surface. One of the ways it looks different is it's much darker. And then when we look at its colors, it's actually redder than the average surface. But we interpret that as good news, because we think dark and red means rich in organics. And we also think that it hasn't been exposed to the space environment for too long. So we're pretty excited that Nightingale actually is something from the subsurface. I think it's a pretty fresh impact crater. And so it's as representative as we can do by collecting a sample from one location on the asteroid surface. And quite honestly, as I hope I convinced you, Bennu didn't give us a lot of choices here. We went in with a certain toolkit to collect a certain kind of sample, and that's what we're going to apply. I'm confident we're going to get a great sample of high science value off the surface of this asteroid. Okay, Laura Bird asks, what determines if the dust particles are launched into space or back into Bennu regarding the ejection events? That really has to do with the velocity. How fast is the particle moving when it leaves the surface of the asteroid? Bennu has an escape velocity, just like the Earth does. If you want to launch a rocket, if you want to launch a spacecraft on a rocket into the solar system, you have to overcome the escape velocity of the Earth, which is about 11.4 kilometers per second. That's really fast, and we need a big rocket in order to achieve that. On Bennu, the escape velocity is 20 centimeters per second. So you don't have to be moving very fast to leave. What's interesting is when we see so many particles coming back off the surface of the asteroid, they're going at less than escape velocity, less than 20 centimeters per second. That's why that energy of the event turned out to be so low. That was one of the biggest surprises. You know, we did all this work. We characterized every particle that was in every image. We tracked its trajectory. We figured out what its launch velocity was. And then we calculated the total energy. And I was like, 100 millijoules. That's like that much energy. So it doesn't take a lot to get stuff off the surface of the asteroid, and most of it's moving very slowly below the escape velocity of the object. Amy Lemke says, during TAG-SAM collection of regolith, what concerns are there about ejected material on the spacecraft, and do the particle ejections give you any clues to what might happen during TAG-SAM? Guys have some great questions here. We've spent a lot of time thinking about exactly this issue. So the good news is the way the spacecraft is designed, that anything that could be damaged by what we call regolith backscatter, stuff that we kick basically right into our face, will be okay. So the solar arrays, if you've seen, like I have on the screen here in the logo of the mission, the solar arrays are actually in the Y-wing configuration, and the active part of the arrays are on top. So they're as far away from the surface as they can get, and if anything hits them, it's not hitting the area that generates the electricity. We have the sample return capsule also pointing down. That's got a very thick heat shield on it. And we're also pretty sure all of the glass and optics of our cameras can handle that kind of impact event. So we've done a very thorough study, and we're confident that nothing that's required to get the sample back to the Earth could be substantially damaged. We did learn a lot about the particle ejections by the TAG-SAM experiment, so it's almost gone the other way from your question, where we took the TAG-SAM simulations and used that information to help us better understand the energies and the particle size distributions for the ejection events themselves. The energy of a TAG event is about 11 kilojoules. So we're going to dump a lot more energy into the surface during TAG than we are seeing in any of the ejection events to date. Daniel Jane says, if you choose a small crater as your sampling site, aren't you worried that your return sample will be contaminated by the impactor? And how will you sort out the impactor from the asteroid? The good news is when something strikes the surface of an asteroid and creates an impact crater, it's moving very fast and it's destroyed, and its destruction creates the explosion. So you actually excavate material from much deeper than even the impactor went into the surface. So it really is excavating material from deeper inside. That said, we do think that there might be fragments of other impactors on the surface of Bennu, and we might bring some of that home. And we're going to look for that. It would be kind of exciting because that'll tell you, it's like souvenirs that Bennu picked up on its journey from the asteroid belt into the inner solar system. And we want to put that journey back together, and fragments of impactors will help us do that. But I think most of what we're going to pick up is actually from Bennu itself. Amy Lemke asks a really nice question. How much did citizen science volunteers aid in the process of sample site selection? Amy, I hope you were one of our Bennu rock counters. So we put out all of our imaging data on a citizen science site called CosmoQuest, and we invited the public to help count those rocks. The students really helped us focus on the Nightingale site and the regions of interest. But in order to get there, we had to count rocks and cross the entire surface of the asteroid. Millions of rocks have been counted by our citizen science volunteers, and they played a large role in helping us select the sample sites. So thank you to everybody who participated in that program. We really appreciate your efforts. All right, let's see how we're doing on time. It's quarter after. I think I can take a couple more questions, and I think that's the end of our program. So I see David Ballard was part of the CosmoQuest team, so thank you for that. Richard Spitzer asked, do you have real-time video during rehearsals and actual sampling? We do not, unfortunately. When we're talking to the spacecraft during sampling, we're not on our high gain antenna, which is that big radio dish you see mounted on the side of the spacecraft. Because we have too many orientation constraints, most importantly, TAG-SAM has to be pointed down towards the surface of the asteroid. And so we're on what's called a low gain antenna, which has a much wider field of view, and as a result, a much lower data rate. And so we will be getting information from the spacecraft at 40 bits, yes, bits per second. So it is a very slow trickle of data that's coming in as it's flying from orbit departure all the way through the checkpoint and match point maneuvers down to the surface. And then we back away, we, as quickly as possible, put the high gain antenna on to the Earth and then start downlinking all the images. So it's going to take us a few hours to a day to get the images down and to produce the kind of movie that you see right here. Okay, I think back to my hosts, I think that is our program for today. Thank you for everybody for joining us today. I hope you learned something new, and I particularly hope that you join us on both August 11th for the match point rehearsal, particularly on Twitter. We'll be live tweeting through that event. And then, of course, October 11th, we're planning a big NASA live event. We're going to be doing that safely with proper social distancing. So there's a chance that's going to be something similar to this, where several of us are in our own rooms presenting that information. But regardless of the situation, we will be broadcasting live throughout TAG on October 11th. And that starts around 10 in the morning Mountain Time. And so it'll be early afternoon into the early evening on the East Coast as those events are playing out. So a nice time for people to follow along. And I'll be there explaining what's happening along the way. So you'll be seeing the same information that I'm seeing and trying to figure out how the spacecraft is doing from that really slow 40 bit per second data rate. And thanks again for everybody who participated today. I really appreciate your interest and your support for the OSIRIS-REx program.